Hello fellow problem solvers, so today we're going to be doing a problem from the 2039 Math Shortlist, problem C1. I suggest you try this problem out for a minimum of half an hour, ideally an hour to an hour and a half, but not more than 2.5 hours. If on the other hand you would like to go along with us, I suggest you take 10 to 15 minutes and play around with the problem and get your first ideas out on paper. This problem is phenomenal if you feel comfortable enough with combinatorics to start solving IMO type problems. So without further ado, let's begin. So in summary, we have the real numbers a1, a2 till ad, all between 0 and 1, and their sum is equal to n. N is a fixed positive integer, and we must find the minimum case such that we can always, no matter what the numbers we have, which satisfy these two constraints, that we can always partition them into k groups such that the sum of each group is less than or equal to 1. Now, what should you do if you don't know how to begin a problem? The answer is play around with small cases. Let's say n equals 1. Well, for n equals 1, it's obvious we will just put k equals 1 because all the numbers can just go into one group. So k equals 1 is the answer, and it's at least one group. So now for n equals 2. Okay, say if these two, then a1 and a2 both need to be equal to 1, so that's uninteresting, then k is at least 2. So for d equals 3, we have, say, a1 plus a2 plus a3 is equal to 2. Now, can we pick these numbers such that k equals 2 doesn't partition them? Oh yes, we can. We can just make them all equal to 2/3. If every single one of them is 2/3, put any two in the same group, and you'll have a sum that's greater than or equal to 1. So that means that k is greater than or equal to 3. And then we play again. So now say, if d is 4, then we have this sum is 2. What can we do here? I don't think we can't really put k equals, we can't force k to be 4 because it seems like we will always be able to put two of these numbers in the same group. So it feels like k is equal to 3 is a solution here. And now I would invite you to pause for maybe 5 to 10 minutes, play around with some other cases and see what idea pops to mind first. And the reason I'm inviting you to stop and play here is because depending on the idea that you get, you will solve the problem differently. So now that you pause, let's move forward. Now, before we continue on with this problem-solving journey with this problem, I would like to point out something general about these types of problems. Namely, it is that they have two parts. The first one is that we need to find the k that always works, meaning that whatever the ai's are and whatever d is in this case, that we will be able to break them up into k groups. And that's the first thing. But the second thing is show that there is a case where that k is necessary, meaning that you can't, here we're trying to find the minimum k, so we need to show that there's a case where we can't use k minus 1 groups, where we need k groups, whatever k is in terms of n. Now the playing around will give you a sense of the second part. What is the case? And it will also sort of hint at what the k is. But for me personally, playing around with n equals, not really 1, but 1, 2, 3, and finding k is 1, 3, 5, this sort of gave me a sense of what the actual answer is. And now we could play around and solve for find that k is equal to, the pattern here is k is 2n minus 1, and we can play around and solve the problem through that. But instead of doing that, I would like to take a little bit of a different approach and sort of show you a different way of solving a problem, not just by playing around with it, but namely by taking a bird's eye view. So the bird's eye view is we have a1 plus all the way till ad is equal to n. And we have some k that we get from this n. Now let's think about what happens when we get n plus 1 instead of n. If we are to look at this problem inductively, say this is a different d, say d prime. Now what is k here? Well, it makes sense, at least to me, somewhat that if we are to take a couple of numbers from a1 till ad prime, such that their sum is greater than or equal to 1, say a subset of them, ai1, i2 till ait, such that it's greater than or equal to 1, but say less than 2. But if we take these numbers such that we can put them into, say, 4 groups that have sum at most 1, then what we would be left with is we would have a1 plus ad prime minus all of these, ai1, ait, and this sum right here would be less than or equal to n, which means that of these numbers that are remaining, we could use this same k, which tells us that there's probably a linear relationship between these. Say if k here is equal to x, here k will be equal to x plus 4 if we need 4 groups. Now this tells us maybe what the shape of k will be. And because we're adding a constant, that means it's going to be a linear combination of n. And now another part of taking a sort of bird's eye view of the problem is to look at different ai's. Namely, if we have ai plus 2 plus ad is equal to n. Now this is, say, one type of problem, meaning we have a specific a1, specific a2, specific ad, which satisfy these constraints. Now sort of an insight here is what happens, say a1 plus a2 is in the same group. That means their sum is less than or equal to 1. Now what does that mean also? Well, it means that if we combine these into some number b1 and make the sum such that b2 is equal to a3 and bd minus 1 is equal to ad, then this is also a set of numbers such that bi is less than or equal to 1 and 0 with some n. It is also a part of our problem. It is just another case in the problem we're trying to solve. Now this bird's eye view tells us that if we have two numbers whose sum is less than or equal to 1, we can just consider merging them, thinking of them as one number, as they are going to be in the same group. And the reason why is because we will have a problem where those two numbers are merged into one. And the same k needs to be for both this one and this one. And now that I've done this sort of back and forth between a bird's eye view and a specific playing around view, I suggest you take 20 minutes and try to solve the problem completely by yourself. And here I would really urge you to pause and try to solve it, because you can come up with all the insights you need to solve the problem by yourself. So now that you've hopefully paused, let's wrap up the problem and put all these ideas together. So now that you've hopefully paused, let's develop these ideas further and go towards a solution. So now let's look at the two parallel ideas. The first one, from playing around, what I got at least, was that I'm looking for numbers which are very close to a half but are greater to a half. And when the idea is to make, when you're trying to have k greater than or equal to 2n minus 1, then the idea really comes very fast. Mainly put these equals 2n minus 1 and have a1 equal to a2 equal to ad equal to n over 2n minus 1. Now the sum of any two ai plus aj is equal to 2a1 is equal to 2n over 2n minus 1, and this is greater than 1. Now this means that every single ai must be in their own group, and because there are 2n minus 1 ai's, that means that k is greater than or equal to 2n minus 1. Now let's look at the merging idea. The question is, when can we merge? So say a1 is greater than or equal to a2, greater than or equal to ad, and their sum is equal to n. What happens if we can't merge? Well, in that case, we can have at most one of these numbers, meaning AD, at most one of them is greater than or equal, is less than or equal to a half, and all the others are greater than or equal to 1/2. What it really means is that AD plus AD minus 1 is greater than 1. This means we can't merge them. Now we keep in mind that we also have k is equal to 2n minus 1 is what we would like to prove. And keeping that in mind, we see that if d is less than 2n, then we are basically done. Like, we just put every single one of these into their own group and we're done. However, if d is greater than or equal to 2n, that presents a problem if we say this. Now, can you take 5 minutes and see the reason why there's a problem if both this, and this is true? Well, the problem is just put them into groups of 2. A1 plus A2 plus all the way till A2n minus 1 plus A2n. This could be AD plus all the way till AD is equal to n. Now, if each of these is greater than 1, then what we will have is that this whole thing right here is going to be n is going to be greater than 1 plus 1 plus all the way till what we have here, 1. This is n ones plus some potential change, which means n is going to be greater than n plus some change, but strictly greater than, and this is a contradiction. Now this, together with what we've done previously, sort of solves our problem, because if d is greater than or equal to 2n, then that implies that we can merge them and get sort of a new sequence of numbers that satisfy these conditions, but with d minus 1. If d is less than or equal to 2n minus 1, well, then we just put them into their own separate groups, k separate groups, k equals 2n minus 1, and we've proved that k is at least 2n minus 1 because we have this case where all the AIs are equal to n over 2n minus 1, and this means we're done. Now, before we write up the problem, I suggest you take 20 minutes and try to, 20 to 40 minutes actually, and try to write up the problem all by yourself, the problem solution, how you would formally write it up in a competition. And also, after you're done with that, and maybe watching this video, I suggest you also go to the official IMO page and find the shortlist from 2013 and this problem, and find their official solutions. So you can see different approaches that they took to come up with different solutions to the problem, which you can then learn from in your further mathematical education. Now, let's write this up. So we first say that for d equals 2n minus 1, and a1 equals to a2 is equal to a2n minus 1 is equal to n over 2n minus 1, we have that no two numbers can be put in the same group, because if they were, their sum would be ai plus aj would be 2n over 2n minus 1, which is greater than 1. So every single one of these must be in their own group, which means that k is greater than or equal to 2n minus 1. Next, we show that k equaling 2n minus 1 is good enough. And we do this via induction on d. For d that is less than or equal to 2n minus 1, we can just put each of the AIs into their own sort of group. But now if d is greater than or equal to 2n, then what we do is we say there exist two numbers. We claim that there exist two numbers, ai and ai plus 1, such that their sum is less than or equal to 1. And we prove this via contradiction. So assume the contrary, assume for every one of these we have a1 plus a2 is greater than 1, so is a3 plus a4, and so is all the way till a2n minus 1 plus a2n. Now this sum right here is by definition less than or equal to n, because there might be some other numbers here as well. But we have, because we assumed the contrary, that this is greater than 1, greater than 1, greater than 1. So the whole thing is greater than 1 plus 1 plus 1. There are n ones here, and then we get this is equal to n. And we get n is strictly greater than n, which is a contradiction. Now this means for these greater than or equal to 2n, there exists two of these, which are ai and ai plus 1, such that their sum is going to be less than or equal to 1. Now assume without loss of generality that a1 plus a1 is greater than or equal to a2 is greater than or equal to a3 is greater than or equal to ad minus 1, greater than or equal to ad, greater than or equal to 0. And now what we say is we know via this that there exists two of them such that they are less than or equal to 1, which means also these two, the sum of these two is less than or equal to 1. So now we can say that we are trying to solve this problem. We're trying to put them into 2n minus 1 groups, but the sequence a1, a2, till ad minus 2, and ad minus 1 plus ad, this is a sequence of d minus 1 numbers, which satisfies such that every one of them is between 0 and 1. And by the inductive hypothesis, we can partition them into 2n minus 1 groups such that the sum of the numbers in each group is less than or equal to 1. This is what we needed to prove, and we are done. And as always, thanks for problem solving.